Hello everyone, and welcome to the Waveshare ESP32 Arduino Getting Started tutorial. In previous lessons, we learned about the ESP32's Wi-Fi functions. Today, we will explore another wireless communication technology, Bluetooth. When you think of Bluetooth, you might think of Bluetooth headphones or speakers. They use classic Bluetooth, a technology suitable for continuous, high-bandwidth data transmission, such as audio streaming. However, for the IoT field, we have a better choice: Bluetooth Low Energy. BLE is designed specifically for IoT applications. With ultra-low power consumption and fast connection speed, it has become one of the preferred technologies for smart bracelets, wireless sensors, and smart home devices. Bluetooth capabilities vary across ESP32 series chips. Most newer models support Bluetooth Low Energy only, while a few models support both Bluetooth Classic and BLE. This tutorial will focus on BLE. We will learn how to use ESP32 for BLE communication step-by-step through 3 examples. Send sensor data from the ESP32 via Bluetooth. Receive phone commands to control an LED on the ESP32. Implement BLE communication between 2 ESP32 development boards. The text version of this lesson and links to the example code are available in the video description. Let's get started. Before writing code, we need to understand 2 core concepts of BLE communication: GAP and GATT. GAP is responsible for Bluetooth device discovery and connection, while GATT is responsible for data exchange after a successful connection. First, GAP defines 2 roles: peripheral and central. A peripheral is typically a device that broadcasts data, such as a sensor or a smart bulb. It advertises its presence. A central is usually a smartphone or computer. It scans for advertisements to find target devices and actively initiates connection requests. Once devices establish a connection via GAP, data exchange is managed by GATT. GATT uses a client-server architecture. Typically, the peripheral that provides data is the GATT server, and the central that requests data is the GATT client. On the GATT server, data is organized in a clear hierarchical structure. At the top is a service, which represents a function of the device, such as a temperature service or battery service. Each service contains 1 or more characteristics. A characteristic is the basic unit of data exchange. It contains a specific value, for example, the battery level percentage. Each characteristic has a set of properties that define the operation permissions, such as whether the value is readable, writable, or can actively notify the client when it changes. To be uniquely identified in the BLE network, each service and characteristic must be assigned a unique UUID. Now let's learn how to use BLE through practical examples. In the first example, we configure the ESP32 as a peripheral, read the analog value from a potentiometer, and send the data via BLE. Then we receive the data using a Bluetooth debugging app on a phone. First, let's build the circuit. You need an ESP32 board, a potentiometer, a breadboard, some jumper wires. Build the circuit according to this diagram. Next, let's take a look at the code. You can find the full source code at the documentation link below the video. First, we include the BLE-related libraries. Next, global variables and definitions. P-server and P-potentiometer characteristic are pointers that will point to the BLE server and characteristic object we create. Device connected is a Boolean flag to track the connection status between the ESP32 and a central device. Then we initialize potentiometer-related variables. Here, we define 2 128-bit UUIDs. UUIDs are unique identifiers for services and characteristics. Each service and characteristic needs a unique UUID. You can use the tool linked in the video description to generate them. Now look at the first custom class, MyServerCallbacks. This class inherits from BLE server callbacks and specifically handles Bluetooth server events. You can think of it as an event listener. We override 2 methods, onConnect and onDisconnect. When a client successfully connects, onConnect is automatically called. We set device connected to true and print a connection success message. When the client disconnects, onDisconnect is called. We reset the flag to false, print a disconnection message, and restart advertising so the device can be discovered and reconnected. Now comes the most important part, the setup function, where we configure BLE. First, we initialize the serial port with serial.begin-to-print debug messages. Then we initialize the potentiometer input. Now the core steps of BLE initialization. Step 1. Initialize the BLE stack and give the device a name. This is the name that appears when a phone scans for Bluetooth devices. Step 2. Create a BLE server instance. Register the callback class we defined earlier with the BLE server so that connection and disconnection events are handled correctly. Create a service as a container for characteristics, passing in the service UUID. Create a characteristic within the service. The first parameter is the characteristic UUID. The second parameter is the characteristics properties. BLE characteristic. Property read means the value can be read. Property notify means it supports notify, i.e., the value can be pushed to the client when it changes. Add the 2902 descriptor so that the client can properly enable or disable notifications. Finally, start the service and start advertising, making the device active and discoverable. Now look at the loop function. The logic here is simple. We check if device connected. We only read and send data when a device is connected, saving resources. After a device is connected, read the current potentiometer value. Next, a simple data filter. We only consider a change valid when the value change exceeds a threshold. If the change is valid, update the value stored in the characteristic. Then actively push the new value to subscribed clients, implementing the notify function. Now upload the code to the ESP32. After uploading, open a Bluetooth debugging tool on your phone, such as Light Blue. Scan for devices in the app, find the device named ESP32_potentiometer, and connect. After a successful connection, find the characteristic we defined. To view the value conveniently, select the data type in the upper right corner, set the byte limit to 2, and set the data type to 2 byte unsigned integer. Click Read to read the data. Turn the potentiometer and read again. Observe the value change. You can also click Subscribe to subscribe to notifications. The values will update automatically when the potentiometer changes. As you turn the potentiometer, the value received on the phone changes in real time. Now let's try the reverse operation. Send commands from a phone to control an LED connected to the ESP32 via Bluetooth. We need to build an LED circuit. We need an ESP32 board, an LED, a 330 ohms current limiting resistor, a breadboard, some jumper wires. Build the circuit according to this diagram. Let's look at the code, focusing on the differences from the previous example. First, we added definitions for the LED and generated brand new service and characteristic UUIDs for this new project. Remember, BLE devices with different functions must use different UUIDs to avoid conflicts. The server callback class is the same as in the previous example, handling connection and disconnection events. This time, we added a new callback class, MyLEDCallbacks. It inherits from BLE characteristic callbacks. Unlike BLE server callbacks, which listens to server events, this is dedicated to listening to events for a specific characteristic. We override the onWrite method. This code is automatically triggered when a client writes data to this characteristic. Inside the method, we use getValue to obtain the data sent by the client. We only care about the first byte, so we take only the first byte. Then, depending on whether command is 1 or 0, we call digital write to turn the LED on or off. Finally, after executing the command, we update the characteristic's own value with setValue, ensuring that when the client reads this characteristic again, it gets the true LED state. Unlike example 1, here setValue receives a pointer and a length as parameters because the setValue function is overloaded to handle different data types. You can right-click on the function name in the Arduino IDE and select Go to Definition to see its various forms. Now look at the changes in setup. First, we initialize the LED pin as output using pin mode. We give the device a new name, ESP32_LED_control, to distinguish it. When creating the characteristic, note that its properties are set to property read and property write. The write property indicates that the client can write data to this characteristic. Then we bind this characteristic to the MyLED callbacks we defined earlier. This ensures that any write operation to this characteristic will trigger our onWrite method. Finally, the loop function. You will notice it is empty. This is not an omission. In this program, all the core logic responding to client commands to control the LED is placed inside the onWrite callback. Upload the code, and again use Light Blue to connect to the device. Find the characteristic, select the data type in the upper right corner, set the byte limit to 1, and set the data type to 1 byte unsigned integer. Click Read to read the initial LED state. Click Write New Value, enter 1, and send. The LED on the board will turn on. Write 0 and it turns off. We have successfully sent control commands from the phone to the ESP32. Having mastered the basics of sending and receiving data, let's challenge ourselves with a comprehensive example. We will use one ESP32 with a potentiometer wirelessly control the brightness of an LED connected to another ESP32. This example requires 2 circuits and 2 sets of code. First, let's analyze the peripheral side code, which is more familiar. This code is very similar to example 2. Both create a writable characteristic to receive commands. Let's focus on the key differences. We generated brand new UUIDs for this new service and characteristic and named the device ESP32_LED. The main difference lies in the data handling logic. In the onWrite method of myBrightness callbacks, when we receive brightness data, we do not call analog write immediately. Instead, we store the data in the global variable brightness and set the new data available flag to true. The actual analog write function that controls the LED brightness is placed in the main loop. The loop constantly checks the new data available flag. Only when new data is available does it update the brightness and reset the flag. Separating data reception from data processing is a common programming pattern that helps avoid performing time, consuming operations inside callbacks, and keeps the system responsive. Now let's focus on the central device B code. This is the first time we use an ESP32 as a BLE client. First, look at the global variables and definitions. These 2 definitions must exactly match the ones in the peripheral code. They are the only credentials for the client to find the correct service and characteristic. Next are several key global variables. DoConnect and Connected are Boolean flags for connection management. DoConnect indicates whether a connection can be established. When the scan callback finds the target device, it sets DoConnect to true. Connected keeps track of whether the device is currently in a valid connected state. pServerAddress is a pointer to store the Bluetooth address of the target device A we found. Premote characteristic is a pointer to the remote characteristic on device A that controls brightness. All subsequent data writes will be done through this pointer. Now look at the first client callback class. MyClientCallbacks. This class inherits from BLE client callbacks and handles connection events of the client itself. We override 2 methods. OnConnect, called when the client successfully connects to the server. In this example, we add no specific logic, but in a real project, you could set flags or print success messages here. OnDisconnect. This method is crucial. It is triggered when the connection to the server is lost. Here, we immediately set the connected flag to false and print a log. The loop function will use this status to decide whether to restart scanning. Next is the second and most important callback class in this code, MyAdvertisedDeviceCallbacks. This class inherits from BLE, Advertised Device Callbacks. You can think of it as a Bluetooth radar callback. Its onResult method is called every time the ESP32 scanner discovers a BLE device that is advertising. Inside it, we add a check whether the newly discovered device's advertisement contains the specific service UUID we are looking for. Once a matching device is found, the code does 3 things. Immediately stops scanning. This is very important. It saves power and prevents the program from being disturbed by other devices discovered later. Saves the address of the target device for later connection. Sets the connection request flag to true. Below is a helper function, connect to server. We encapsulate all the complex connection steps here. This function receives a device address as a parameter and returns a Boolean indicating whether the connection succeeded. As the first step of acting as a client, create a client instance. Register the client connection callbacks we defined earlier, so disconnection events can be handled. Attempt to connect to the target BLE server using the address. If the connection succeeds, we still cannot communicate immediately. We must first find the service and characteristic we want to operate on. Look for the service on the remote server by its UUID. After finding the service, use getCharacteristic to obtain the specific characteristic we need from that service. After all steps succeed, set the global connected flag to true and return true. If any step fails, the function returns false. Finally, let's look at the loop function. The loop function is divided into 3 parts. The first part is connection management. It continuously checks the flag set by the scan callback. Once it becomes true, it calls connect to server to attempt a connection, and after success, clears the flag. If the connection fails, it waits 3 seconds and then restarts a short scan. The second part is data processing and sending. Executes after a successful connection. First, Read the potentiometer value. Then, use map to convert the 12-bit ADC reading to an 8-bit brightness value. Again, to reduce unnecessary communication, we only send when the brightness change exceeds a set threshold. When the change exceeds the threshold, send the brightness data. The third part is reconnection, the else section. If currently not connected and there is no pending connection request, it means the device is disconnected, so it restarts scanning to let the program automatically try to recover the connection. Upload the two pieces of code to their respective boards. The boards will automatically connect. You can also connect to the serial monitor to view debug messages. After a successful connection, try turning the potentiometer on board B. You will see the brightness of the LED on board A change accordingly. Well, that's it for this lesson. Let's quickly recap. We learned the basic concepts of BLE. GAP handles connection management. GATT defines data structures. We learned how to set up a BLE peripheral to send sensor data to a phone. We learned how to receive BLE data to control hardware. Finally, we implemented BLE wireless communication between two ESP32 devices. This concludes this tutorial series. To help you consolidate what you have learned, we have prepared some interesting hands-on integrated projects in the documentation, combining knowledge from previous sections. We invite you to read them and try them out. Wishing you smooth development and the creation of your own brilliant works. Thank you for watching, and see you in the next series.